the simple analogy is if you throw a stone in the water, it produces these waves. Similarly, if something moves really fast in the universe, if two things collide really quickly, they produce these ripples. These are called gravitational waves, and we can learn a lot about the universe if we can detect them, analyze them. That's what we do. So I work at the intersection of the theory and the instrumentation, in the sense that the instrumentation groups, they provide us with the data, and the theories they give us the models for the gravitational wave signals. They look like these waves with some wiggles, and what we do is test the theory against the data. But the first step to do this is first to detect this signal in the data. And once you have detected the signal, you also want to learn about the parameters, like where in the sky the signal came from, how far it was, what were like the source properties of of the systems that emitted the signals. So I work on data analysis, which is essentially extracting some physics related insights from the data provided by the instrumentalist. Yeah, the research is about how to quickly separate signals and the glitches, and how to also do it accurately. And again, I will give an analogy to explain this. For example, let's say you are walking in a railway station with your friend, and the friend is talking about something. So that something is the signal, because you really want to hear what your friend is telling you. And the glitches is all the random noise that you can hear. If the trains pass and if they make a whistle, that's a glitch. There's actually something called a whistle glitch. If the dogs are barking, that's also another type of glitch. If the children are crying, that's also another other type of glitch. If somebody screams, all those things, that is. So everything except your friend's voice is a glitch. And this is separate from the background noise, because even if there were no glitches, there's also a constant humming at the railway station, for example. This is the background noise that you can't distinguish. So there are three components: the signal, the background noise, and the glitches. And the thesis goes over how you can quickly and accurately remove these glitches, because otherwise, if you can't remove the glitches, you can't detect the signals. Specifically, the Einstein telescope and the triangular design of it has a very unique property. The triangle it's actually a network of three detectors. There's one detector, if this is a triangle, there's one here, there's one here, one here. So one detector at each corner. So it's a network. And to solve the problem of glitches, we use the geometry of the triangle. Now, the good thing about the triangle is that if you just add the data from detector 1 plus detector 2 plus detector 3, it cancels out the signal. And this is a really good thing, because imagine you have this like three time series from detector 1, detector 2, detector 3. You add them all up, the signal cancels. This you know for sure, because this is a geometric property. But now what's remaining is pure noise, and there are also glitches in there. So you can pick them up, you can quickly remove them from the mainstream, and then you get your pure signal back. So in the sense, this is how we do it, and this is much quicker than the state of the art, and it's also accurate, and this is what we find in the simulation. And this property of adding data streams to cancel the signal is unique to the triangular geometry of the Einstein telescope, and that's why it has a clear edge over the other proposed geometries.